So last time we started into organic chemistry, hydrocarbons. And just want to review a little bit of our naming. As promised, I do have rules for you. So there's actually two different sheets. I'll give these to you when we get to the next chapter, because these rules are for next chapter. But I will give these to you today. And we'll do just a little bit of practice before we move on. Okay, take a look at that. I'll give you just a minute. See if you can come up with a name for it. See if you can come up with a name for that.
I mean, no. To
the octane
2595 65 no.
with the octane trig method.
Is that better? Which one is it? Well, but there's a
Go up,
longer one
right?
that goes up to 8.
Yeah, it's go up to 8. So it's octane. So then we do the 1, 2, 3 is trig method. Oh. Okay.
I don't know. I just drew it. I didn't name it first. So, anyone have a name they want to say, and then we'll figure it out. Okay. What is the name you want to suggest?
2, 5.
Oh, wait.
6.
Try to.
Okay. What have you got?
So I got 1, 2, 5, trig Matthew or Metro, and octane.
Okay. Well, neither one of those is 100% correct. So let's work it out. First, we need to find our parent chain. So if we start here, we can go 1, 2, 3, 4, 5, 6. So that's 7. But if we go 6, 7, 8, that means That is our parent chain. Okay. So we are dealing with octane. And we do have 1, 2, 3 methyl groups. So it is trimethyl. So the only thing that we need to adjust here is our numbering. So we can either number from here 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7, 8. So it can either be 2, 5, 6 or 3, 4, 7.
3, 4, 7. 3, 4, 7.
Remember, we want the lower numbers. So, okay. Like I said, mostly this is going to be practice. Okay. So, practice. I will give you some resources to help you practice, in addition to the homework, because homework practice too. But I'll give you some extra stuff that if you'd like to work on, you can do that. Anyway, today, kind of like I said, we're going to start with the basics and build off of them. Today we're going to add another little wrinkle to this, okay? We're going to deal with alkenes and alkynes. Alkenes and alkynes. So just like we had an alkane, everything ended with A-N-E. We have an alkene. Guess what it's going to end with?
E-N-E.
E-N-E. And if we have an alkyne,
Y-N-E.
So, the question is, how do you know if you have an alkene? And it's actually really, really simple. There's a double bond. Okay. We are now going to introduce unsaturated hydrocarbons. We have a double bond. Now, this is the simplest alkene. We cannot have a one carbon alkene because to have a double bond, you have to have 2 carbons. But the rules are going to be very, very similar. So how many carbons are in this?
2.
2. So what is the prefix for 2 carbons?
No.
F. So our prefix is F, and it ends with E-N-E. So what is this?
Alkene.
Ethene.
Huh?
Ethene.
Ethene.
Ethene. Okay? Ethene. With our stick diagram, this one's really easy to draw. Okay. You will see a lot of times, to make sure that people know you're not talking about an equal sign, you'll see people put in the hydrogens on ethene. But yeah, so for a double bond, we use 2 lines. So what if we had something like that? How many carbons do we have? 4. Okay. So what is the prefix for 4 carbons?
But
Bute.
Bute.
Okay. So we have butene. But wait. Is that not also butene?
No. Yeah. No. Yeah.
It is. Are these the same thing?
Yeah. No.
No.
No. What's different about them? The double bond is in a different place. So while this is also butene, they are different. But you already know how we're going to differentiate them. What do we use to tell the difference between these two?
What do you mean?
What are we going to put in the name? A number. And what is that number going to tell us? Where the double bond is. This is 1 butene. Okay? Because if we number from here, 1, 2, 3, 4, the double bond starts on carbon 1. Okay? That's 1 butene. What is this one?
2.
2 butene. What's that one?
1.
1.
Oh.
Remember, you can count from the other side. So I have butene here. 1 butene. Okay. But if we flip it around, it's the same molecule, didn't change anything. Now it fits with that. It's still 1 butene. Ooh, what about that one?
Can I go get my book?
2.
What? One,
We can have more than one double bond.
2, 3, 4.
So we still have 4 carbons. We still have 4 carbons. So
1, 3.
okay, you were really, really close.
1.
So it is 1, 3.
Butene. No, butane. What is that?
Butadiene.
Why?
Diene. It's 2.
I am dying.
Yeah. Yeah.
So is that just when it has?
It has 2 double bonds.
Is it 2 or more, or just 2 double bonds? Oh, because di.
Di means 2. Yep.
Oh, wow.
So what would it be if there were 3?
Trace bond.
Triene. Okay, it would end up being a triene. Sure it is. It's in the paragraph right there.
Oh, maybe I should highlight that.
Now, here is,
But why is it 1 and 3?
Tells us where the double bonds are. Okay. One nice thing about having this is that it will be our parent chain. Even if there is something longer without this, without the double bond. So for example, if we were to say that, okay? Now we can make a longer chain using this. 1, 2, 3, 4, 5, 6, 7. But that excludes the double bond. So that is not our parent chain. Okay? The parent chain has to include the double bond. So our only options are 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6. Okay? So that's something to remember. Your parent chain has to have the double bond in it. Of course, just like alkanes, our alkenes can be branched. Luckily, we already know the rules about naming branched compounds. Okay. So let's just make sure we understand that. We're going to look at example problem 3 right here. Okay. So this is what we have. So how many carbons are in our parent chain? 7. Okay. So we know we're dealing with a heptene. What else do we know?
There's 2 that.
Okay, so we have dimethyl.
Dimethyl.
2 and 4.
Okay. The numbering also gets easier
Oh.
because it doesn't matter about these. What matters is making that number as low as possible.
Oh.
So all you care about, make the double bond as low as possible. So we're going to number from this side.
1, 2.
4 and 6.
So this is going to be 4, 6, and this is 2. So our name becomes 4, 6, dimethyl,
What happened to
2,
2 after
heptene.
combine? I don't think I'm more complicated.
Well, everything we do from here on out, we're going to add another possibility to name. So.
Are we doing 2 sections here? Just 1. Oh, why? No, just 1. You think that much information is going to stick into our head?
Yeah, because these are actually, we're pretty much finished with the first section. Because, guess what? If we have an alkyne, it is exactly the same, except we replace ene with ine. Okay? So if we have a triple bond,
So that's 1.
So how many carbons are in this chain?
1,
1, 2, 3, 4, 5. Okay.
10,
So you start from the
10.
1 pentyne. Once again, we know that we have to start on that side because we need to make the number for
No.
the triple bond as low as possible.
That makes it easier
Doesn't matter what else we have. I could put an ethyl group or a methyl group right here. Doesn't matter. It's still going to be 4
Yeah.
methyl. Okay. I can put an ethyl group right there. 3 ethyl, 4 methyl, 1 pentyne. Okay. So yeah, that's section 3. See, not so bad. And guess what? Section 4,
It's the same.
we're going to deal with first some double bonds.
though. Okay.
So,
I'm
well, actually, I guess double bonds, we're going to get to them in just a second. First, we need to introduce this concept of something called an isomer. Isomer. Yes, 2 or more compounds. They have the same chemical composition, but different structures.
I knew that from the top of my head.
I'm very proud. So let's look at C4H10.
Wow.
It's a big
Okay.
one, like,
It's not that big.
I mean, number 2.
Okay. So if we have 4 carbons and 10 hydrogens, you can arrange them like that. All right. We can also do that. We have 1, 2, 3, 4. And we are still going to have, so this is going to be CH3, 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 CH. So we still have our 10 hydrogens. But we can also that is fine. Here. There we go. We'll do C5 because that gives us another one. So that gives us another way. If it were the C4, we can only do it 2 ways. C5, we can do it this other way too. So we have 5 carbons. We still have 12 hydrogens. So, anytime you add more carbons, you can do more structural isomers. Okay. So 4 carbons gives us 2 different ways. 5 carbons gives us 3 different ways. 6. I can't remember off the top of my head. 7 has 9 though. And once you get to 20 different carbons, there are over 300,000 different structural isomers that you can make. Okay. So the key is we have the same number of, or we have the same chemical formula, but we're putting things slightly different. Okay. That's what we have with an isomer. So as promised, let's talk double bonds. So if we have this lovely little butene, if you have a carbon-carbon bond, in all actuality, this can rotate like this, and it does. Okay? A single bond can rotate, and they move around. Okay? They do that. However, once you get a double bond, it no longer rotates. And that is why we have to address this issue of stereoisomers. So normally, when we write these structures, so you have these nice up and down, up and down, up and down. Okay. But remember, this can rotate. So there's really nothing wrong with writing it like that. Now, we don't like it. It looks weird, but it's exactly the same. But a double bond, if we put a double bond here, then it has to stay that way. Or it also can flip around and be the other direction. And it will stay that way. Once the molecule has formed, it stays in that orientation. Okay. This is a subtle difference, but it does make a difference. And so there's one extra little thing that we need to add into our naming. We need to say, is it like this or is it like this? And we have a pretty easy, it's pretty easy to determine. Okay? So what you're going to do, you take the double bond here. And this, okay, we count 1, 2, 3, 4, 5, 6. Doesn't matter which side we count from, 1, 2, 3. Okay? So both of these are going to be 3-hexene. Okay. If you put your hand over the double bond, okay, the carbons that come off of that double bond, are they on the same side of my hand or are they on different sides? They're on different sides. It goes across the hand, right? You see that, everyone? Because one is down here and one is over here. So we call that, because it goes across the double bond, trans 3-hexene. If you do that and they are on the same side, you want to see how they're on the same side of my hand there? Okay. That is cis 3-hexene. Okay. Anytime you're dealing with double bonds, there's a possibility of needing to put either cis or trans in there. There are a couple of instances where it doesn't make any sense, where you wouldn't need to do it. And really, it's when going across or on the same is identical. So with ethene, doesn't matter. Anywhere there's going to be a hydrogen. So this really isn't, it's not possible to have a different isomer, okay? Because they're all the same. Same thing with propene, okay? You can't have a different isomer. But once you get to butene, then you can have that different structure. Kind of the same thing if it's at the end. If your double bond is at the end, you have two hydrogens, and so it doesn't really matter. You can't say that one is cis versus trans. So anyway, so that's just one little tiny thing to add into your naming of double bonds. Okay. Are we all thoroughly confused? Really, it's just a matter of, if you have a double bond, determine whether those carbons come off the same side or off opposite sides of the double bond. Okay, that's really all it is. When I grade, like especially on tests, basically what happens is this would be like 4 points. Okay, so you get 1 point for that, 1 point for this, 1 point for this, and 1 point for that. Okay, and so if you forgot that, well, you'd still get 3 out of 4 points. Okay. Yes. So if you can get at least some of the parts right, you're going to get some points. Okay. I definitely do not do an all or nothing grading on the names. Okay? If you can get some of the components in there, even if you can just get the parent chain right and write, like if you just wrote hex, you'd get a point because yeah, that's part of the name. Okay? So there's a lot of points to be had with naming. So make sure, even if you're not 100% sure of the name, put what you can. Okay? Put what you can. All right. Let's try a little bit more practice with this, and then there's just one more concept that I want to talk about today. One more concept. Okay. Take a second and on your own, see if you can create a name for that. what have you got?
So 5. Oh. Yes, 5C5. 6, 7. 3, 10.
That. Very, very close. We're just missing one thing.
Oh.
Train.
But other than that, very good. Like I said, that would get a lot of points on the test. So, yeah. Okay. So the last type of isomer that we need to discuss is, well, it's the idea of chirality. And this is kind of an interesting concept. So basically, what we're looking at when we are dealing with chiral molecules is mirror images, but not just mirror images. We're looking at non-superimposable mirror images. So what in the world does that mean? Have non-superimposable mirror images. Well, look at your hands. Okay. If you were to take your right hand and hold it up to a mirror, it looks like your left hand is there, right? Okay. But can you take your right hand and put it over your left hand and have them match up perfectly? So if you put it this way, thumbs are on the wrong side, but the thumb on the right side, well, all of a sudden the palms are switched. They're not identical. Okay. So your hands are chiral. Okay. They're mirror images. They have the same things. Okay. The same things on both hands. They're mirror images, but you can't put one on top of the other and have it be exactly the same. Now we have molecules that can do this, okay? And that, I thought I had them made already, but I guess not. So I'm going to pop this together and make an example for you. Okay. So here, notice, got the black in the middle. We have red, we've got green, we've got blue, we've got purple. Okay. So these are isomers. They are exactly the same as far as what is in them. They're also mirror images. You see that? Okay. There was a mirror right here. This is what you would see in the mirror. But there is no way to get them to line up. Okay. Here we have the purple and the green, red and blue are switched. Well, if we fix that to get the red and blue, in the right spot. It's going to flip our purple and our green. Okay. There is no way that you can move these around and they'll be exactly the same. They are chiral. Now this makes a difference in a lot of biological systems. Sugars. Sugars have a bunch of what we call chiral centers where they're made of the same thing, but you flip a couple things around the other side and it's a completely different molecule. If you were to somehow go to a different universe where all of the sugars were flipped to the opposite molecule, so this is what you were normally eating, but then you went to a universe that had all of these sugars, even though there would be plenty of food for you to eat, you'd starve to death because your body doesn't know how to work with this one. It's kind of weird. They're identical, except your body is set up to only work with one of them. And there's a lot of examples like that. Now, I'm not saying every chiral thing your body can't handle both, but a lot of them. It's set up to handle only one. So there are naming rules with that, but we're going to ignore that. Okay? I'm not going to ask you to look for chiral centers and name them, because basically what you have to do is start looking at these individual, I mean, obviously these colors, they can be all sorts of different things. And so you have to have a whole second set of rules to determine which one is the most important, and then the second most important, and then you have to say, okay, is it going around to the right or is it going around to the left? And it's annoying. Okay. So we're going to ignore that chiral centers exist when it comes to naming. Okay, so don't stress about that. But if you ever see something that has a D or an L in the name, if you ever look at something, it's describing chiral centers. Now, if you ever want to identify if a molecule has chiral centers, this has been hanging on the wall all year and nobody has ever said, hey, what's that? What's that? What's this? Great question.
Is that the cycle?
Yeah, I'm not going to ask you to name this because it's got all sorts of functional groups and yeah. Honestly, I don't even know the name off the top of my head, the official IUPAC name. I'd have to sit down and work it out. And most likely I would just look it up. So, but what this actually is adrenaline.
Oh, okay.
This is adrenaline, okay? Or epinephrine. And this has a chiral center right there. This is one chiral carbon. Okay? Happens to be the only chiral carbon in this entire molecule. Now, how do you know? Well, number one, it has to be attached to 4 different things. Okay? So if you're ever looking for a chiral carbon, anything that's not attached to 4 different things, not chiral. So this one right here, it's attached to this carbon, and that hydrogen. It's got that double bond. So we know that can't be chiral. In fact, all of the carbons in here are only attached to 3 things because it's a benzene ring. We haven't talked about benzene, so don't worry. That's one section that we just don't have time to get into.
Okay.
So, but it's section 5 in this chapter if you're interested. Aromatic compounds. A little bit of fun reading. So now this carbon here, it is attached to 4 different things. So we have 1 carbon, 1 nitrogen, 2 hydrogens. So 4 separate bonds there. This one is also attached at 4 different places. So 3 hydrogens and that nitrogen. But the reason why this one is chiral and the others are not is that all 4 are unique. So on this section, we've got this whole benzene ring compound. This one right here, we've got hydrogen. This one right here, we have an oxygen and a hydrogen. And this one right here, we've got this carbon, nitrogen, carbon. Okay? So all 4 of those different things, or all 4 of the bonds, are to different things. So I could make a different carbon, or a different isomer of this by switching a couple things around. Okay. So if I did that, it's now the other chirality. Okay. And I believe that adrenaline is one of those things that your body cares about the chirality. I'd have to double check that. Anyway, so today we introduced unsaturated hydrocarbons. Okay? Alkenes and alkynes. The naming, remember, it's based off of the rules that we established last time. The differences are our suffix ends, depending, or our suffix changes, depending on do we have a double bond or a triple bond. Okay. The parent chain has to have the double or the triple bond in it. We number where the double or triple bond is, and our numbering makes that as low as possible. Okay. The other ones don't matter. Okay. The other ones don't matter. Like this molecule, yeah, 2 is lower than 3. So if we didn't have that double bond right there, we would start numbering from here. And we would have 2 and 3 for our dimethyl and 4 for our ethyl. But that double bond changes things. The double bond is more important than any of the other things when it comes to numbering. Okay. So. And as far as isomers go, like I said, if we have the double bond, just be aware of it. Okay? If you can put your hand on that double bond and they come off of opposite sides, it's trans. They're on the same side, it's cis. Okay? Questions? It really is a matter of practicing. I know we're throwing a bunch of rules at you. The only way you're really going to get comfortable with them is practicing, doing the homework. There are online resources, other things. Like I said, I can give you some good resources to practice if you are interested. Anyway, so obviously I have some homework for you because I know how much you love homework.
Can I go to the bathroom?